I now have the pleasure of introducing tonight's first scientific maestro, Dr. Shikma Bressler from the Department of Particle Physics and Astrophysics. In her experiments, Shikma finds that, like in music, the very basic units of matter, rather than being Lego blocks, are vibrations and excitations of fields and strings. Stay tuned for the music of the universe.
Okay. Good evening. My name is Shikma, and I'm a particle physicist. I know this is a bad opening line. Sometimes it's enough to say I'm a physicist to introduce a lot of stress. Now, Alon will tell you shortly everything about stress, and I really don't want to take you there now. Honestly, there is no need to. Because in my field of research, we are asking a very simple question. We simply ask, what is the universe made of? Or what are the fundamental building blocks of the universe? Now, this question accompanies humanity since the day we started asking questions, at least since the day we started asking scientific questions. So in this respect, our research is just the current step of a journey that started with the idea that everything is made of earth, wind, water, and fire, followed by the understanding of the concept of table of elements, the discovery of the atom, proton, neutron, electron, and so on. Imagine what would have been missed if we had stopped anywhere along this line. So what do we know today? Where did this quest take us? With the help of the orchestra here, I will try explaining it to you. Are you ready? Okay. So we know that there are 18 fundamental particles. Each one has a unique set of properties, which in the orchestra will be represented by a unique sound. Let's hear them. We also know, and this is really important, how these particles interact. Of course, the analogy between the orchestra and particle physics is imperfect. For example, in the orchestra, each particle has a different size, while in physics, all the particles have no size at all. In fact, if we could squeeze the universe, but really, really squeeze it, we would have get a handful of nothing. Now, I have said this sentence so many times in the past, but still I find it so strange that most of what we see around us is actually a result of particle interactions. Now let's try understanding this idea with some more concrete example. Here is the electron. It is the particle responsible for electricity. Here it is in our orchestra. Let's hear its representation for this evening. You may have also heard about the positron. It is identical to the electron in all the aspects, but has an opposite electrical charge. I assume you all heard about the photon. Have you? Good. So, the photon is the particle that is sometimes referred to as the particle of light. Let's hear it in the orchestra. As in the orchestra, the electron and the photon do not belong to the same family, so they have completely different characteristics. Now let's hear what happened when an electron and a positron interact. What happened here? When the electron and the positron collided, they annihilated each other. Both disappeared, and instead, we got a photon. Well, in real life, in such a process, we will get 2 photons, but I will leave it for the next concert. I hope it's okay. Okay? You could also see it, by the way, on the screen. The electron and the positron moving toward each other, annihilating into a photon. Let's hear it again. So we know that there are 18 fundamental particles, and we know how they interact. The thing is that we think that something else is out there. We think so because the theory that tells us about the 18 particles, what we call the standard model of particle physics, is incomplete. For example, it explains only 5% of the mass of the universe, and we know very little about the origin of the remaining 95%. Or we don't know why there are so many electrons in the universe, however, so few positrons. And there are many more mysteries like that. And besides, when we write down the theory, it looks like that. Now, I would like to believe, and it really doesn't matter what I believe in, that the theory that describes everything will be a little bit more elegant than that. Okay, so far, I tried explaining why we think that we should be looking for physics beyond the standard model. It is a bit harder to explain, but we also think that if there is physics beyond the standard model, then there should be new particles, and that these particles should be massive. So what do we do to check this assumption? How do we move forward toward what we hope will be our next discoveries? We lean on Einstein, who once wrote the most famous equation in the history of science. He wrote E equals mc squared. For us, that means that if we put a lot of energy in one point, so if E is large, we can actually get something very massive. So M can be large as well. And this is exactly what we are currently doing with the Large Hadron Collider at CERN. Following Einstein equations, we convert energy to mass. We accelerate protons, which are relatively light, give them a lot of energy, hoping that when we collide them, something massive will be produced. Now, if something massive is produced, it immediately decays into the standard model particles. We measure the outcome of these collisions with the Atlas detector, which here at Weizmann, a large and important part was built, hoping to discover something new. Now, of course, this is not the end of the story, because new and exciting things are very rare. So rare that in order to increase our chance to produce them, we do not collide one proton with one proton. Instead, we collide bunches of 10 to the 11 protons with 10 to the 11 protons. We do it 40 million times a second, and we hope to do it in the next 20 years. This is unbelievable. As I told you, and I hope that you can also hear, that in most of this collision, we produce just the standard model particles. And on top of this, what we call huge standard model background, we try to find a signal, which we have no idea how it looks like, or even if it exists. So how do we do it? We try to reduce the standard model background, hoping to reveal a signal. Can you reduce the background for me, please? As you just heard, in most of the time, in fact, in all of the time so far, we reduced the wrong background and found nothing. Now, in reality, these attempts are really challenging. Sometimes they take years to be completed just to find out, well, nothing. Now let's try reducing another background. Again, we find nothing. We hope that in one of these attempts, nature will cooperate, and we will finally hear a new sound. Now, my musical skills are fairly limited, but I can really imagine how one new sound can serve as an inspiration for an amazing symphony. If we found something beyond the standard model, our symphony will give us deeper understanding of our universe. Perhaps it will be a new theory that answers some of these unanswered questions I mentioned earlier. Or even better, a theory that answers questions we never dreamt of asking. תודה רבה. תודה רבה.